Okay, we are solving problem 76 from chapter 5 of Giancoli 6th edition. Okay, so what they give to us in this problem is the radius. So they give us the radius of a banked curve and the speed that this curve was designed for. Okay? Which means if you enter with that speed that is given to you in the problem, you will be able to make this curve without any friction. So it's the perfect speed. Okay? We found an equation, and remember, as I said, you need to know how to derive that equation. So we found an equation that connects the angle of the banked curve, the angle theta, with that speed and that radius. Okay, so I'm going to use this equation here to find the theta, but remember you are supposed to know how to derive this equation. Okay, so I use this equation for my given radius and for my given speed, I find the theta. So we know theta in this story. And then the question comes, what is the range of speeds that we can enter this curve and still safely make it? In other words, what they want to know is, what is the maximum speed that you can enter this curve and still make this curve without flying away? And what is the minimum speed that you can enter and will not slide down? So these are the questions. What is the maximum and what is the minimum? Okay. So let's draw and go for the equation. So this is our inclined, our bank curved. This is the angle theta that we already found. I'm going to put my car here. It has mg pointing down. It has normal force. It's touching this surface. And if I had entered with the perfect speed, this would be the only forces. I wouldn't need friction force. But I enter with high speed. And what is my tendency? Well, I tend to fly away from this curve. What is going to prevent my car from doing that? Well, friction force. Okay, so this is too bad. Let's make it a little better. Friction force against that tendency to fly away. Okay, static friction force. All right, let's go for the other one. This case here, again, the same angle that we already found. I put my car here. We have mg. We have the normal force. And if we enter this curve with a tiny speed, our tendency is to slide down. Okay, what is going to prevent this from happening? The friction force against it. Friction force, and this is static. Okay, so this is what we need to know to now try to solve the problem. Okay, so remember, this is a circular motion. The centripetal acceleration is pointing in this direction. So the best frame to use is this one. So this is the y, and this is the x. This is the best one because I will not need to decompose the centripetal acceleration. So this is the x and this is the y direction. Let me do the same here. This is the x and this is the y direction. Okay, now let's go. Let's think about the angles so that we can decompose our vectors. Angle theta is here. Okay, so it's also here. If it's theta is here, well, opposite is also here, theta. Fn is perpendicular to the surface, so this one is 90 minus theta. And x and y are perpendicular, so this one is theta. Let's go to the other side. This is theta, this is also theta. Opposite is theta. Fn is perpendicular to the surface, this is 90 minus theta. X and y are perpendicular, so this has to be theta. Okay, so let me start from the left side. I want to find the maximum speed. I'm going to start writing the equations in the y direction. Okay, in the y direction, let me pick this triangle here. Let me erase this angle here. And let me pick this triangle here for decomposing the Fn. So I'm looking at the y direction. In the y direction, the Fn is, the component in the y direction is adjacent to the angle. So I'm going to write Fn cosine of theta is positive because it's pointing up. Okay, so this is the triangle we are looking at. Okay, what else do I have? I have this friction force here, and what I'm going to do is I'm going to play with this triangle here. So this is in the x direction and this is in the y direction. See that in the y direction I am opposite to the angle. So this is going to be minus the friction force, and here I'll put sine of theta because it's opposite to the angle. And we also have the mg, minus mg. In the y direction, no motion, so this is 0. Okay, let me give some space here and let me write the equation in the x direction down here. In the x direction, there is no weight, there is no mg. I have just the components of Fn and of the friction. The component for the Fn is this one, opposite to the angle, so it's going to be Fn sine of theta. The component for the friction is this one, adjacent to the angle theta here, so this is going to be plus, it's pointing towards the x direction, the positive direction, so it's plus friction, and this is cosine of theta. Nothing else, no other force, so the sum of all this is ma, and a is the centripetal acceleration, so v squared over r. This v is the maximum, okay, that we want to find. Okay, to find this maximum, this is my unknown in this story, I need to try to isolate Fn. But I also see the friction force. Well, not too bad, because I know that the friction force is related to Fn. The friction force is mu Fn. Okay? So if I remember that, I'm going to come to this equation. Instead of friction force, I'll write it as mu Fn. So you see that this equation in the y direction becomes Fn cosine of theta. And then I also have minus mu sine of theta. And this is equal to mg. So now I isolate Fn. Fn is equal to mg divided by cosine of theta minus mu sine of theta. Very good. Let me isolate this. I isolated Fn. Let me keep this in a box. And I'm going to use this now in the x equation. Okay, let me go for the x equation. I have Fn sine of theta. Let me already put that the friction force is mu Fn. Okay, so we have that Fn multiplied by sine of theta plus mu cosine of theta. All this is equal to m, the v that we want to find, the v maximum squared divided by the radius. Okay, so I isolated Fn. Let me put this here. All right, so what I have now is mg cosine of theta minus mu sine of theta. This is the Fn. Multiply by all that sine of theta plus mu cosine of theta. On the right side, I have m, my unknown, which is my v max, and this is squared divided by r. Okay, everything here we have except the maximum speed that we are after and the mass. But do not worry, because the mass here cancels. So everything else that you have in this equation now is numbers that you have. So you just enter these numbers and find the Vmax. Okay? Okay, once you found the Vmax, let's go to the other side of this problem, which is to find the V minimum, the minimum speed. Well, things are very much equivalent now. What is the only difference in this graph, in this sketch for the minimum speed? The direction of the friction force. The direction of the friction force for the maximum was pointing along the ramp, pointing down along the ramp, and here it's pointing up along the ramp. That's the only thing. So the only thing that will change in the equations is the sign of the friction force. Let me just put this explicitly here. In the y equation, I still have the Fn in the same position, so it's still again Fn cosine of theta. Now, if I look at the friction, I'm going to use this triangle here. Okay, so I play with this triangle here. All right, and for this triangle here, What do I have? That the y component of the friction is opposite, so it's going to be a sign, just as it was before, but it's pointing up. So that's the only difference in this story. I will have now a plus friction force sine of theta. And mg is still the same, minus mg equals to 0. If I go for the equation in the x direction, what will change? Well, Fn is still positive, okay, so I'm going to put Fn, and it's Fn sine of theta here, and this is the Fn in the x direction, okay, so it's opposite to the angle. And how about the friction force? Well, the friction force is this component here, adjacent, so it's a cosine, and it's pointing in the negative direction. So that's what it changes here, is minus the friction force cosine of theta. Okay, so everything is pretty similar, and this is going to be mv, and this v now is the minimum, squared divided by r. So the equations are very similar. You do the same procedure that you did before. The only thing that is changing is this sign here and this sign here.